Good day everyone and welcome to our presentation. We are Colby Banbury, Emil Nior, Matthew Stewart, Pete Warden, Manjanath Kudler, Nat Jeffries, Xenophon Fafudis, and Vijay Janapa Reddy. Today, we're excited to share our research titled Wake Vision, a large-scale, diverse dataset and benchmark suite for TinyML person detection. We've tackled the challenge of evaluating TinyML models, proposing a new benchmark suite for a more holistic analysis. Stay tuned as we delve into the implications of our findings and their potential to revolutionize TinyML research. In this slide, we delve into the key motivations and problem statements of our study. We address the critical challenge of accurately evaluating machine learning models. It's important to note that the performance of a model on a basic test set can often be misleading, not truly reflecting its real-world performance. This discrepancy is particularly pronounced in TinyML use cases, where model compression is a necessity. Our study also highlights the lack of standardization in evaluating performance on the VWW dataset. This lack of uniformity makes it difficult to compare works based on the dataset, as performance differences can be attributed to factors outside the work's contribution. In essence, our work is motivated by the need to bridge the gap between test set performance and real-world performance, and to establish a standardized evaluation method for the VWW dataset. This will enable a more accurate and fair comparison of different models and techniques. In this slide, we delve into the key insights and contributions of our study. We've discovered the critical role of real-world use cases and deployment environments in model design. It's not just about how a model performs on a test set, but how it fares in the real world. Our benchmark suite is a powerful tool in this regard. It allows for a more comprehensive analysis during the design phase, helping to identify the right circumstances for applying TinyML compression techniques. In terms of contributions, we've proposed a benchmark suite that enables holistic analysis during the design phase. We've also suggested a standard model for data-centric contributions and a standard pre-processing pipeline for model-centric contributions. These standards will help streamline the evaluation process and make comparisons more meaningful. In essence, our work is about making machine learning models more effective, efficient, and applicable in real-world scenarios. In this slide, we delve into the key highlights of our method. We've established a pre-processing pipeline that includes several steps. First, we cast the image pixel value data type from 8-bit integers into 32-bit floating points. Then we resize and crop the image to match the model input size. Following this, we normalize pixel values between -1 and 1 on a sample-wise basis. The final step involves using the image tensor as input features and the person label as the target feature. This systematic approach ensures consistency and comparability across different models and datasets. It's a crucial part of our work, enabling both data-centric and model-centric improvements. Stay tuned as we delve deeper into the practical implications of these methods in the following slides. In this slide, we delve into the key results of our research. We present a case study that explores the impact of TinyML scaling, underscoring the significance of fine-grained analysis. We also discuss how we utilize the benchmark suite in our scaling experiments, employing TinyML compression techniques. Moving on to the author's message, we want to emphasize the importance of a holistic approach when it comes to model design and evaluation. We believe that the benchmark suite is a valuable tool in this process, enabling a more comprehensive analysis during the design phase. In essence, our research highlights the need for careful consideration of real-world use cases and deployment environments in TinyML. We hope that our findings will guide ML practitioners in making informed design decisions and contribute to the advancement of TinyML. On this slide, we delve into the fascinating world of TinyML. This emerging field is all about reducing energy consumption and cost in machine learning deployments. It's a game changer, especially in an era where efficiency is key. Take a look at the image on the screen. These are sample images from the Wake Vision fine-grained benchmark suite. They represent diverse and challenging scenarios used for evaluating TinyML model performance. TinyML is unique in its approach. It co-locates machine learning models with a suite of fine-grained benchmark sets. This allows for a more comprehensive evaluation of a model's fairness and robustness in various settings. In essence, TinyML is about making machine learning more accessible and efficient without compromising on performance. It's a field that's set to revolutionize how we approach machine learning deployments. As we delve deeper into the world of machine learning, we encounter unique challenges. One of the most significant is the discrepancy between the performance of ML models on basic test sets and their performance in real-world scenarios. This issue is particularly pronounced in the field of TinyML, where we often need to balance accuracy with model performance and size. Take a look at the figure on the screen. These are sample images from the Wake Vision Fine-Grained Benchmark Suite. They demonstrate the diverse and challenging scenarios we use for evaluating TinyML model performance. In TinyML use cases, we often see a domain shift. This means that the conditions under which the model was trained and tested can differ significantly from the conditions it encounters in the real world. For instance, a person detection system might work perfectly in well-lit conditions, but fail in darker environments. These challenges underline the importance of a more holistic approach to model evaluation, which we'll explore further in the next slides. On this slide, we delve into the impact of design decisions on TinyML models. It's crucial to understand that even minor decisions can have a significant effect on real-world performance. For instance, a model's performance might seem satisfactory during testing, but it could falter in real-world scenarios due to factors like lighting conditions. This is why it's essential to consider the deployment environment during the design phase. The image you see here showcases sample images from the Wake Vision Fine-Grained Benchmark Suite. These diverse and challenging scenarios are used to evaluate TinyML model performance, ensuring that the models are robust and fair. As we delve deeper into the world of TinyML, we encounter a significant issue with the Visual Wake Words, or VWW, dataset. The lack of standardization in this dataset makes it challenging to compare different works based on it. This is because performance differences can often be attributed to external factors, such as the pre-processing pipelines used, rather than the actual contributions of the work. To illustrate this, let's take a look at these sample images from the Wake Vision Fine-Grained Benchmark Suite. These images demonstrate the diverse and challenging scenarios we use for evaluating TinyML model performance. This diversity and complexity are crucial for developing robust and fair models. In this slide, we're diving into the heart of our proposed solutions. We're introducing a benchmark suite that allows for a more comprehensive analysis of TinyML models. This suite is designed to evaluate a model's fairness and robustness in diverse and challenging scenarios, as demonstrated by the sample images from the Wake Vision Fine-Grained Benchmark Suite shown here. We're also proposing a standard model for data-centric contributions, which will help to streamline the process of integrating new data into our system. Additionally, we're introducing a standard pre-processing pipeline for model-centric contributions. This will ensure that all models are evaluated on a level playing field, regardless of their individual complexities. These solutions aim to address the challenges faced in TinyML deployments, particularly the trade-off between accuracy and model performance and size. They also highlight the importance of considering real-world use cases during the design phase. On this slide, we delve into the crucial aspect of our study: the pre-processing pipeline. This pipeline is a series of steps that prepares our images for the TinyML models. First, we cast the image pixel value data type from 8-bit integers into 32-bit floating points. This allows us to handle a wider range of pixel values. Next, we resize and crop the image to match the model input size. This ensures that our models receive consistently sized inputs. We then normalize pixel values to a range between -1 and 1. This step is crucial for maintaining consistency and avoiding bias in our models. Finally, we use the image tensor as input features and the person label as the target feature. This allows our models to learn from the images and predict the person label. The figure displayed here showcases sample images from the Wake Vision Fine-Grained Benchmark Suite, demonstrating the diverse and challenging scenarios used for evaluating TinyML model performance. In our exploration of TinyML, we've seen how this emerging field of ultra-low power machine learning is revolutionizing the way we deploy ML models. The primary goal here is to significantly reduce energy consumption and cost, making machine learning more accessible and efficient. Now, let's delve into the specifics of TinyML compression techniques. These techniques play a crucial role in our scaling experiments. They help us strike a balance between accuracy and model performance, a trade-off that is particularly important in real-world use cases. For instance, consider a person detection system operating in low light conditions. The test dataset may not have enough dark samples, leading to a discrepancy between test accuracy and real-world performance. This is where TinyML compression techniques come into play, helping us optimize the model for such challenging scenarios. Remember, the goal is not just to create models that perform well on test sets, but to design systems that are robust and reliable in the real world. And that's the power of TinyML. Begin a frame. Frame title our approach and results. Begin itemize. Item our solution. Benchmark suite. Begin itemize. Item enables holistic analysis during design phase. Item assesses models' robustness in challenging settings and across demographics. End itemize. Item comparison with visual wake words. Begin itemize. Item trained identical models using VWW and our Wake Vision datasets. Item achieved 0.5% improvement on VWW's test set and 2.41% improvement on Wake Vision's test set. End itemize. Item benchmark suite usage. Begin itemize. Item helps determine if a model is accurate in the planned deployment setting. Item assists in making design choices based on use case specifics. End itemize. End itemize. End a frame. In our exploration of related works, we've identified two key areas of focus. Firstly, we've seen that previous approaches to model and data-centric contributions can often skew results. This is due to differences in pre-processing pipelines, which can lead to inconsistencies when comparing works based on the same dataset. Secondly, we've recognized the need for a benchmark suite. This suite is crucial for a more holistic analysis during the design phase. It allows us to evaluate a model's fairness and robustness in challenging settings, which is particularly important in the field of TinyML. Furthermore, this benchmark suite aids in identifying the appropriate circumstances for using TinyML compression techniques. This is a significant step forward in ensuring the real-world performance of our models, especially when we have to trade off accuracy for model performance and size. In summary, by addressing these two areas, we can make strides towards more reliable and effective TinyML deployments. In this slide, we delve deeper into the technical aspects of our research. Our work primarily addresses the challenge of accurately evaluating machine learning models in TinyML use cases. We've identified a significant discrepancy between basic test set performance and real-world performance. This discrepancy is due to two factors: domain shift and model compression. The figure you see here illustrates the effects of scaling the image size versus the model width on test accuracy and the distance far benchmark set. It's clear from this visual representation that the distance far F1 score is highly sensitive to changes in the image size compared to the overall test accuracy. Furthermore, it shows the impact of image size and MobileNet V2 width multiplier on the model performance. In essence, our research aims to bridge the gap between theoretical performance and practical application in TinyML, ensuring that models perform as expected in real-world scenarios. In this slide, we delve into the technical details of our research. The figure you see here illustrates the effects of scaling the image size versus the model width on test accuracy and the distance far benchmark set. It's a visual representation of how changes in image size and the width multiplier of MobileNet V2 impact model performance. Now, let's talk about the problem formulation. We've identified a significant issue: the domain shift between test data and real-world use cases. This discrepancy can lead to misleading performance evaluations. Furthermore, we've noted the absence of a standardized method for evaluating performance on the VWW dataset. This lack of standardization makes it difficult to compare different models and techniques. In the next slides, we'll discuss our proposed solutions to these problems. Stay tuned. In this slide, we delve into the technical details of our proposed method. We've introduced a benchmark suite that allows for a more comprehensive analysis during the design phase of machine learning models. This suite is particularly useful in identifying the impact of various factors on model performance, as illustrated in the figure. The figure shows the effects of scaling the image size versus the model width on test accuracy and the distance far benchmark set. It's clear that the distance far F1 score is highly sensitive to changes in the image size compared to the overall test accuracy. This highlights the importance of considering specific use cases when designing models, as the image size can have a significant impact on performance, especially when the subject is far from the camera. Furthermore, we propose a standard model for data centric contributions, and a standard pre-processing pipeline for model-centric contributions. This standardization aims to facilitate fair comparisons between different works and contributions. In essence, our proposed method provides a more holistic approach to model design and evaluation, taking into account both high-level metrics and specific use case scenarios. In this slide, we delve into the technical details of our proposed method. We've established a standard model for data-centric contributions, which is a MobileNet v2 model with a width modifier of 0.25. This provides a consistent basis for evaluating the impact of data-centric improvements. For model-centric contributions, we've proposed a standard pre-processing pipeline. This includes casting image pixel value data type from 8-bit integers into 32-bit floating points, resizing and cropping the image to match the model input size, normalizing pixel values between -1 and 1, and using the image tensor as input features with the person label as the target feature. The figure you see here illustrates the effects of scaling the image size versus the model width on test accuracy and the distance FAR benchmark set. It shows the sensitivity of the distance FAR F1 score to changes in the image size compared to the overall test accuracy. It also visually represents the impact of image size and MobileNet v2 width multiplier on the model performance. This is crucial for understanding how different factors can influence the performance of our models. In this slide, we delve deeper into the technical aspects of our research. The figure you see here illustrates the effects of scaling the image size versus the model width on test accuracy and the distance FAR benchmark set. It's interesting to note that the distance FAR F1 score is more sensitive to changes in image size compared to the overall test accuracy. This figure also provides a visual representation of the impact of image size and MobileNet v2 width multiplier on the model performance. Our experiment design is based on the VWW dataset. We conducted a series of scaling experiments using typical TinyML compression techniques. This approach allowed us to explore the trade-offs between model size, image size, and performance, particularly in challenging settings such as when the subject is far from the camera. These findings are crucial for ML developers, as they can inform design decisions for specific use cases. In this slide, we delve into the technical details of our research. The figure you see illustrates the effects of scaling the image size versus the model width on test accuracy and the distance FAR benchmark set. It's interesting to note how the distance FAR F1 score is sensitive to changes in the image size compared to the overall test accuracy. This figure also visually represents the impact of image size and MobileNet v2 width multiplier on the model performance. Now, let's talk about how we evaluate our results. We use accuracy as the primary metric for the overall test and validation set. This gives us a broad understanding of how well our model is performing. For the fine-grained benchmarks, we use the F1 score as the primary metric. This allows us to measure the balance between precision and recall, which is crucial in many real-world applications. This dual approach to evaluation ensures we have a comprehensive understanding of our model's performance. In this slide, we delve deeper into the technical aspects of our research. The figure you see here illustrates the effects of scaling the image size versus the model width on test accuracy and the distance FAR benchmark set. It's interesting to note the sensitivity of the distance FAR F1 score to changes in the image size compared to the overall test accuracy. This figure also visually represents the impact of image size and MobileNet v2 width multiplier on the model performance. Our research presents a case study on the effect of TinyML scaling, emphasizing the importance of fine-grain analysis. We've used the benchmark suite in scaling experiments, employing TinyML compression techniques. This approach allows us to identify the circumstances under which these techniques are most effective. In essence, our findings suggest that for ML developers targeting use cases where the subject is likely to be far from the camera, prioritizing larger input image sizes over wider models may be more beneficial. This is a critical design consideration that could be obscured when solely relying on high-level metrics like overall test accuracy. Our distance benchmark effectively unveils the disproportionate impact of image size on model performance for distant subjects, enabling more informed decision-making during model optimization. Moving on to our technical results, let's take a look at this figure. It illustrates the effects of scaling the image size versus the model width on test accuracy and the distance far benchmark set. What's interesting here is the sensitivity of the F1 score to changes in image size. This underscores the importance of fine-grain analysis in TinyML scaling. Now, let's recap the key findings from our paper. We presented a case study on TinyML scaling, emphasizing the need for fine-grain analysis. We found that basic test set performance can often misrepresent real-world performance. This is due to factors like domain shift and model compression. We also demonstrated the usefulness of our benchmark suite in scaling experiments with TinyML compression techniques. This suite enables a more holistic analysis during the design phase, helping us identify the most appropriate circumstances for these techniques. These findings are crucial for the TinyML community as they shed light on the challenges and potential solutions in scaling TinyML models. Moving on to our technical results, let's take a look at this figure. It illustrates the effects of scaling the image size versus the model width on test accuracy and the distance far benchmark set. What's interesting here is the sensitivity of the F1 score to changes in image size. This emphasizes the importance of fine-grain analysis in TinyML scaling. Now, let's delve into the implications of these results. Firstly, they underscore the need to consider real-world use cases and deployment environments in ML model design and evaluation. It's not enough to just look at basic test set performance. We need to consider how the model will perform in the real world. Secondly, there's a clear discrepancy between basic test set performance and real-world performance. This highlights the need for comprehensive evaluation methods. We can't just rely on a single metric or test set. Lastly, our benchmark suite proves to be a valuable tool for ML practitioners. It aids in design decisions and ensures better real-world performance. So, it's not just about creating a model that performs well on a test set. It's about creating a model that performs well in the real world. In conclusion, this research addresses the critical need for accurate evaluation of machine learning models, particularly in the context of TinyML. We've introduced a benchmark suite that allows for a more in-depth analysis during the design phase, enabling us to better understand the impact of design decisions on real-world performance. We've also proposed a standard model and pre-processing pipeline for data-centric and model-centric contributions respectively. This standardization allows for more meaningful comparisons between different works and helps to isolate the impact of the actual contributions. Furthermore, we've presented a case study on TinyML scaling, emphasizing the importance of fine-grain analysis. This case study demonstrates how TinyML compression techniques can be appropriately applied under different circumstances. In essence, our work provides a robust framework for evaluating and improving machine learning models, especially in the realm of TinyML. We believe that this will significantly contribute to the development of more efficient and effective machine learning deployments.